In this video, we are going to talk about Newton's method. Newton's method is a way of approximating the values of the x-intercepts for a function. And so to kind of motivate this, what we're doing is we're trying to find the value such that f of x equals 0. So we're trying to find the x value where this happens. And if we just look at a graph of a function, say we have the following function here. And so this value here is what we're trying to find. We're trying to find the value of that x value. And so we're going to call that r, just so we have something to refer to. And so the idea in Newton's method is that we pick a guess. So we're just going to pick some point that we think is about the correct value. So I'm going to say it's right here. It's going to be x1. This is just some value that we're selecting kind of as an initial guess. Now what we do in Newton's method is we go up on the graph to the point on the graph with that x coordinate. So the point x1 comma f of x1. Okay, and so we just find that point on the graph, and then we take the line tangent to the function y equals f of x at that point. And so we're going to find the tangent line, which looks something like the following. And this tangent line, assuming that we didn't pick a place where we had a critical number, which we'll talk about what happens in that case in a minute. So assuming we didn't do that, this tangent line will intersect the x-axis somewhere. And so it intersects somewhere, and we're going to call this point x sub 2. And then the idea is that if x sub 2 is closer to our approximation than x sub 1 was, then we have a better guess. So x sub 2 is better than x sub 1 at approximating r. And then we just repeat this process. And so we go up to this point on the graph x sub 2 comma f of x sub 2. Draw the tangent line at this point now. And notice that this also has an x-intercept, which x-intercepts of lines are very easy to find. That's why we use these tangent lines. So this would be some value x sub 3. And now notice x sub 3 is really close to the value of r, but we could get even closer if we went up again to this point right here, x sub 3 comma f of x sub 3. We could form the tangent line there, and we basically get the value of r from that tangent line. And so this process usually doesn't exactly give you r, but in theory it could. And so this is the idea of Newton's method, is this idea of we're just going to take an initial guess, and we're going to use tangent lines, find the x-intercept of the tangent line, and then from there we have a new approximation, then we just repeat this process. And as we keep doing this, we will approximate the value of the x-intercept. So let's look at an example of what we're actually doing here. So we're going to look at an actual function. So we're going to take the function f of x equals 2x cubed minus 3x squared plus 2. And we want to find the third approximation using Newton's method for f of x equals 0, starting with x sub 1 equals negative 1. So we're going to take negative 1 as our initial guess, and we're going to do 3 approximations here. And so what we need to do is we need to find the tangent line. And so remember, the slope of the tangent line is the value of the derivative at that point. So we need the derivative of f. The derivative of f will be 6x squared minus 6x. And so 6x squared minus 6x is our derivative. Now we want the tangent line at the point x sub 1, which is negative 1. So we want f prime of negative 1. which is 6 times negative 1 squared, plus or minus 6 times negative 1. So we get 6 times 1 minus negative 6, so plus 6. So we get 12. And so we have that f of minus 1 is 12. And so this is then the slope of our tangent line. But we're going to use the slope, the point slope form of a line, so we also need to know what f of 1 is. So f of negative 1 is 2 minus 1 cubed minus 3 minus 1 squared plus 2. And then this becomes negative 2 minus 3 plus 2, so we get negative 3. And so what we're doing is we're going to find the tangent line to the point negative 1 comma negative 3 on f of x. Okay, so using the slope, point slope form of a line, we're going to have y minus y1 equals m, which is the slope, which is 12 times x minus x1. So we have y plus 3 equals 12x plus 12. And then solving for y, we get y equals 12x plus 9. And now our value for x sub 2 comes from using this. So we just want to know when this equals 0. That'll be our value for x sub 2. So we have 0 equals 12x plus 9. Minus 9 equals 12x. So x is going to be minus 9 over 12, which is minus 3/4. Okay? And so we get minus 3/4 for our value of x. And so this then is our x sub 2. So if we actually look in our picture, what we've done is our x sub 1 here. I'll actually draw another picture. What we've done here is we've got this function, and I'm just going to draw a random graph. I'm not claiming this is what it looks like. And we're trying to approximate this value of r, and so we started with the value of, say, negative 1 right here. I made this pretty steep, so I'm going to say negative 1's right here. And so that was our x sub 1, and then what we did is we took the tangent line at that point, and this was our x sub 2, which was minus 3/4. And so that's what we've done. We found our tangent line. This blue line that I've drawn is the line y equals 12x plus 9. And then we found its x-intercept, which is minus 3/4. And now we're going to do this process again. So now the benefit of doing this process again is we already know the derivative. So we want the derivative at minus 3/4. So we're going to have 6 times minus 3/4 squared minus 6 times minus 3/4. So this is going to become 6 times 9 over 16 plus 18 over 4. So we get 54 over 16 plus 72 over 16. So we're going to get 108 over 16. And so that is our slope. And then we need to find the value of f at minus 3/4 as well. And so this is going to be 2 times minus 3/4 cubed minus 3x squared minus 3 minus 3/4 squared plus 2. Now rather than computing this, as I did not compute this ahead of time, I'm just going to actually plug it into the formula. So the formula says we're going to have y minus y1, which is f of minus 3/4. This equals the slope, which is 108 over 16 times x minus x1, but x1 was now our 3/4. And then we want to solve for this value of x here. And so we have y equals 108 over 16 x plus, multiplying this out, we're going to get 324 over 64 plus f of minus 3/4. And then we set this equal to 0. So 0 equals this. Like I said, I didn't compute what minus f of minus 3/4 was ahead of time. Now solving for x, what we get is x is going to be equal to 324 over 64 plus f of negative 3/4 divided by 108 over 16. And this is approximately negative 0.6825. So this is the value then of our x sub 3 from doing this process. Now with Newton's method, what we tend to do is, rather than actually doing the whole finding the tangent line every time, because finding the x-intercept of the tangent line involves the same process every time, we just think of a singular formula for it. And so if we know x sub 1, we find x sub 2 by doing y minus f of x sub 1 equals the slope, but the slope is f prime of x sub 1 times x sub 2 minus x sub 1. And then we set y equal to 0, because we want the y-intercept. So we get 0 minus f of x sub 1 equals f prime of x sub 1 times x sub 2 minus x sub 1 times f prime of x sub 1. Then we solve for x sub 2, and so we're going to have x sub 1 f prime of x sub 1 minus f of x sub 1 divided by f prime of x sub 1 equals x sub 2. So we're just solving for x sub 2, so we added the x sub 1 f prime of x sub 1 over, and then divided by the f prime of x sub 1. Now, simplifying this a bit, we get that x sub 2 is equal to x sub 1 minus f of x sub 1 divided by f prime of x sub 1. And so this gives us a formula that tells us from one iteration to the next what we do. And so we just take our original x sub 1 minus f of x sub 1 divided by f prime of x sub 1. And using this formula, we can avoid actually finding the tangent line and just immediately go from one step to the next by plugging in x sub 1, x sub 2, and so on. And so usually the way Newton's method is written down is it's written down as x sub n plus 1, meaning the nth plus first stage is equal to x sub n minus f of x sub n divided by f prime of x sub n. So we're going to look at an example using this formula now, which kind of expedites the process that we just went through. Okay, and so now we want to start with x sub 1 equals 2 to find the third approximation x sub 3 to the equation x cubed minus 2x minus 5 equals 0. So in this case, we're applying Newton's method to the function f of x is equal to x cubed minus 2x minus 5, which has a derivative of 3x squared minus 2. And so now what Newton's method tells us is that we can just use this formula that we derived above, x sub n plus 1 equals x sub n minus f of x sub n divided by f prime of x sub 1, to get what x sub 2 is. And so x sub 2 will be equal to x sub 1 minus f of x sub 1 divided by f prime of x sub 1. X sub 1, though, is 2, so this is just 2 minus f of 2 divided by f prime of 2. And so plugging things in, we're going to have 2 minus 2 cubed minus 2 times 2 minus 5 divided by 3 times 2 squared minus 2. And if you simplify this, you get out a value of 2.1. And so what that tells us is that x sub 2 is equal to 2.1. And so that is the y-intercept for the tangent line to this function, x cubed minus 2x minus 5. at the point 2. But now we wanted to find x sub 3. We wanted the third approximation. Well, x sub 3 equals x sub 2 minus f of x sub 2 divided by f prime of x sub 2, which equals 2.1 minus f of 2.1 divided by f prime of 2.1, which equals 2.1 minus 2.1 cubed minus 2 times 2.1 minus 5 divided by 3 times 2.1 squared minus 2, and this is approximately equal to 2.0946. And so that gives us an approximation for the x-intercept to this function. Now, when doing this process, typically you will need to use a calculator to do the more complicated things. The real benefit of knowing Newton's method is this is how calculators actually give you these approximations. And so when you are using a calculator to approximate some value, like if you are trying to find the x-intercept on a graphing calculator, it gives you the value by just doing Newton's method a ton of times. Now, Newton's method does have a bit of a drawback to it, in that if you pick a bad starting point, we can run into issues. And so, just as a warning, in some situations, the values x sub 1, x sub 2, and so on will not converge on the value r. And so this then means that if it's not converging on it, you need to pick a better x sub 1. This means pick a better starting guess. Because remember, we guess on the first thing. We're guessing x sub 1, and if we're getting values that are not converging, we just need to pick a better starting guess. As a general rule, if the values of x sub I are getting further away from the solution, you need a better guess. Okay, so if your values are getting further away from where the solution actually occurs at, you need a better guess. Now, the issue with this is you might not know the exact value of the solution, but you probably have an idea of the value of the solution. So for instance, in a polynomial, in something like x cubed minus 2x minus 5, you do know that when you plug in the solution, you should be getting 0. And so if the value you get from Newton's method is a larger value than what you got the previous one, you probably have picked a bad starting point. Now, graphically, what is happening here is the following. And so we could have a graph that looks something like the following. And let's say that our x sub 1 value that we pick is right here. And so this is x sub 1. And our tangent line up here is right there. If we draw our tangent line, looks like this. So our x sub 2 value is all the way over here. But notice where the value we're trying to approximate is. R is right here. And so clearly x sub 2 is further away than x sub 1 from R. And so that was a bad initial guess. Now, as a kind of a good way to pick these values is the closer you are to a critical number, usually the worse the guess is. So if you are picking something that's really close to a critical number, that's probably a bad initial guess. You don't want to be very close to critical numbers. Because notice what happens at a critical number in this situation. I'm just going to use this graph from above. If I pick this critical number right here, then when I draw the tangent line is not going to have an x-intercept. And so as long as you don't pick a critical number, you will have an x-intercept. But if you're close to a critical number, your x-intercept is probably getting further away. So you want to avoid critical points when using Newton's method. That's another reason why finding critical points can be helpful, as it can help us know what values we don't want to pick when doing Newton's method. Okay, so now with Newton's method, we can approximate things up to a certain amount of accuracy. And so if we want to use Newton's method to approximate a value correct to, I'm going to say 8 digits, so 8 decimal places. We repeat using the process until we have consecutive approximations that are the same for the first 8 values, 8 decimal values. So basically just keep using Newton's method until you get 2 answers, one after the next, 2 approximations, one after the next, that are the same up to 8 decimals. Now this is actually what a calculator does. So a calculator can do Newton's method very quickly. It's very easy to program a calculator to do Newton's method. And so it just keeps doing Newton's method over and over until it gets 2 consecutive things that are within 8 decimal places, and then it gives you that as the answer, which is why calculators give you accuracy up to 8 decimals usually. You can go up beyond 8 decimals. You can go however many you want. Just in terms of storage, if you have 8 decimals correct, that's usually sufficient for most situations. But if you need more, you can just keep doing the same process. So let's look at an example. And so we want to find the solution to the equation cosine of x equals x, correct to 6 decimal places. Okay, and so we're trying to find the solution to cosine of x equals x, correct to 6 decimal places. Now the way we do this is we rewrite it so it's an x-intercept question. And so what we're going to do is having cosine of x equal x is the same as cosine of x minus x equals 0. And so our f of x is going to be cosine of x minus x. And now when cosine of x minus x equals 0, that's our solution. And so that's what we're going to work with. And so we also need our derivative. So the derivative here is going to be negative sine of x minus 1. Then Newton's method's equation, or formula, is x sub n plus 1 will be x sub n minus f of x sub n divided by f prime of x sub n, which will equal x sub n minus cosine of x sub n minus x sub n divided by negative sine of x sub n minus 1. And so this is then the expression that we're looking for. Now we can simplify this by multiplying everything by negative 1 on the bottom, since they both have a negative. So this is x sub n plus cosine of x sub n minus x sub n divided by sine of x sub n plus 1. So I've just pulled a negative 1 out from the denominator. Okay, and so that then is the expression that we are working with. And so what we're going to do here is we're going to take this expression and we're just going to repeatedly use it until we get approximation. But now we don't know our initial guess, and so what we're going to do first is figure out what's a good initial guess. So if we actually draw the graph of cosine of x, it looks something like the following. And if we draw the graph of y equals x, it looks something like the following. Now we know this value is at pi over 2, and we know this value is at 0, and pi over 2 is about 1.7, so our solution is around 1. So this value is between 0 and 1.7, so our initial guess is going to be 1. Now 1 may not be right. In fact, it's not right. Cosine of 1 minus 1 is not 0. But 1 is a good initial guess, because it's somewhere in the middle. And so we're going to start with x sub 1 equals 1, because that is close to the right answer. And now we're going to find x sub 2, and so on. So x sub 2 will be equal to x sub 1 minus, plus cosine of 1, cosine of x sub 1, minus x sub 1 divided by sine of x sub 1 plus 1, which equals 1 plus cosine of 1 minus 1 divided by sine of 1 plus 1. And computing that value, because we want to be correct to 6 decimals, this is about 0.75036,387. And so I've actually kept more than 3 decimals here. I've kept 6 decimals. I've kept 8 decimals. So that's our x sub 2. And now for x sub 3, we're going to do the same thing. X sub 3 is equal to x sub 2 plus cosine of x sub 2 minus x sub 2 divided by sine of x sub 2 plus 1. And so this approximately is equal to 0.73911,289. So now x sub 4 is going to be equal to x sub 3 plus cosine of x sub 3 minus x sub 3 divided by sine of x sub 3 plus 1, which is approximately equal to 0.73908,513. Now notice that these two solutions still differ in the first 6 places. They're not the same in the first 6 places. They're the same for the first 3, but not the first 6. And so we're going to go another step. We want to keep going until they are the same to the first 6 decimals. And so we have x sub 5 is x sub 4 plus cosine of x sub 4 minus x sub 4 divided by sine of x sub 4 plus 1. This is approximately 0.73908,513. And notice that is the same as x sub 4 for the first 6 decimals. In fact, it's the same for the first 8 decimals. And so that is then our approximation. And so our approximation is that the solution to cosine of x equals x, correct to 6 decimals, is 0.73908,513. Now this is actually correct to 8 decimals because you get to 8 decimals kind of for free. And so this then would be the approximation. And so we were able to approximate that value just by using Newton's method here. Now Newton's method can also be used to compute the value of irrational numbers. And so we're going to look at an example of that. So we're going to use Newton's method to approximate the sixth root of 2 correct to 8 decimals. Now, what we're going to do here is the exact same process that a calculator would do to give you the approximation for the sixth root of 2. And so the first thing to note is that the sixth root of 2 is a positive solution to the equation x to the sixth minus 2 equals 0. The way you see this is we set x equal to the sixth root of 2, but raise both sides to the sixth power, so we get x to the sixth equals 2, and then x to the sixth minus 2 equals 0. And so we're literally just setting x equal to the thing we care about, and then rearranging it to get 0 on one side. And so that's how we get the equation that we want to work with. Now that we have our equation that we want to work with, we're going to do the same thing we did a second ago. Our f of x is equal to x to the sixth minus 2. F prime of x is 6x to the fifth. And so that tells us x sub n plus 1 is equal to x sub n minus f of x sub n divided by f prime of x sub n, which equals x sub n to the sixth minus 2 divided by 6x sub n to the fifth. And so this is the formula. It's x sub n minus that. This is then the formula that we're just going to keep plugging things into. Now we want an initial guess. For an initial guess here, notice that 1 is about the right answer. If we plug in 1, we get out negative 1 from this equation. 1 to the sixth minus 2 is negative 1. And so 1 is about right. It's not quite the right answer, but it's kind of close. And that's the idea that we use with guessing, is we take some value that's kind of close to the right answer and then go from there. And so x sub 1 is going to be 1. That's our initial guess. Then x sub 2 is going to be equal to x sub 1 minus f of x sub 1 divided by f prime of x sub 1, which is 1 minus 1 to the sixth minus 2 over 6 times 1 to the fifth, which is 1 minus negative 1 divided by 6. And so plugging those in, we get 7/6. So x sub 2 is 7/6. And then we want x sub 3. So x sub 3 is going to be equal to x sub 2, which is 7/6 minus 7/6 to the sixth minus 2 divided by 6 times 7/6 to the fifth. And this is approximately equal to 1.1264438. And now I haven't written down what 7/6 is, but this is approximately 1.166666667. And so notice they differ in the first 8 places, and so we need to go again. And so x sub 4 is equal to x sub 3 minus x sub 3 to the sixth minus 2 over 6 times x sub 3 to the fifth. And this is approximately equal to 1.1224977. Okay, notice that these two values differ by in the first 8 places, and so we need to go again. They're correct to the first 2. Well, I guess the first 3 if you count before the decimal. And so we need to go again, though. So x sub 5 is x sub 4 minus x sub 4 to the sixth minus 2 divided by 6 times x sub 4 to the fifth. And this is approximately equal to 1.1224625. Notice this is the same for the first 4 decimals, but we want the first 8, so we need to go again. So x sub 6 is x sub 5 minus x sub 5 to the sixth minus 2 divided by 6 times x sub 5 to the 5th, which is approximately equal to 1.12246,205. And notice these are the same up to 8 decimals. They're the exact same for what I've written down. And so that tells us that the 6th root of 2 is approximately equal to 1.12246,025. So that is our approximation to 8 decimals. And so that then gives us a way of computing these irrational values.